Alright, so today's kind of a follow-up to the breadboard computer videos I put up before. Obviously everything here probably looks really different than what we had going on before. Over here is kind of what we're going to be talking about in today's video. Everything here and over we're going to ignore. This stuff here is the ALU, some control logic, some memory, other stuff that's not too important for today. I've disconnected all of this from here. This is the output section of our computer. It takes an argument from memory and outputs it to a user in a standard hexadecimal output. So, that being said, here's kind of an overview of what we have going on. My computer runs on 4-bit instructions and 4-bit arguments. So we have two 4-bit registers. I take up to 8 bits technically, because we could have some overflow from an operation in the ALU. My multiplication of 2-bit 4 numbers could potentially give you an 8-bit number. We could have a negative 5-bit number. We could have just a 5-bit number from overflow from addition. Shifting can give you 6, 7, 8 bits. So I'm able to take in two 4-bit arguments, each into a register, and then I use a multiplexer to select one of the two registers and put its value, which is 4 bits, put its value made up of 4 bits through a 4-bit decoder, which just turns those 4 bits into a 7-segment display number. So it only does one of these at a time, and then it puts this value into all 4 7-segment display bits. Then I take a oscillator, and the oscillator is either high or low, and it's the control logic to the multiplexer, so it changes rapidly which register is being selected from. And then I also take that output and I run one to one 7-segment display. I invert a copy of it and put the other one to the 7-segment display. So when the clock is high, it might let A through and it would enable the 2nd bit. And when it goes low, it might let B through and it would enable the 0th bit. And it rapidly switches between the two so that I can put a different number in each bit. So I'm only decoding one number, but I'm able to show you several bits, and pretty soon I'm just going to change that oscillator to a 4-bit shift register, and we'll be able to turn on these other two LEDs if I wanted to do that for any reason. So how it works is this is my input output here. I put some dip switches on here, but normally I just connect this part straight to my main computer bus, and I take arguments from there, and here's a control logic to read new values into the register. I can also just clear the values out of the register. But anyway, I could put 0, 1, 1, 0 into the high bits and use the 0, 1, 1, 0 in high, and that's a 6. Then I could put 1, 1, 1, 1 into the low register, which is 1, 1, 1, 1, which is F. So the values are held in memory here, so I can individually clear one and not affect the other, or not. But essentially I take two 4-bit numbers, put them up here into one of two high or low registers, and I'm able to ultimately output a 8-bit or 1 byte display, and hopefully soon we'll be up to 2 bytes or 16 bits. So this drawing here kind of shows you how these breadboards are constructed. So up here is our 4-bit register, RAM, whatever you want to call it. Here's another 4-bit register. I believe I have it high and low. Both of these registers feed into my multiplexer, which is this guy up here. So 2 registers feed into a multiplexer. This multiplexer puts a bunch of stuff onto a bus, which is here, and decodes it through here, 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 here. As you can see, decoder, 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 decoder. And then we have some buses here, just because everything needs to play with the bits. As you can see, once it gets decoded, it gets a 4-bit input, has a 7-bit output. we send each of the LEDs a result. So decoder, decoder, bus, bus. So here's our bus, these strips here, and they all feed through these 7 lines here into the display. Now we only want to show which number is correct on the corresponding LED, otherwise we can only show the same number on both. So we have an oscillator, which is just this little dude right here. It's a pretty simple rapid oscillator, and that oscillator is just that half of the breadboard. And there we go. We got our input outputs and our binary output, hexadecimal output. And that's that. Now I know a lot of people like to use the EEPROM for the decoders. There's some other videos that do that. This computer is about using transistors or discrete components such as diodes, resistors, everything like that. Most EEPROM comes as a integrated circuit or standalone component. So as far as my computer goes, that's cheating for me. So I have to kind of build the decoder myself. So the decoder logic's actually pretty simple. We have 4 bits input. I create an inversion of each of the 4 bits. So I have a 4-bit number and a 4-bit number that's inverted. And then all I do is I use AND gate logic to convert the 4 bits into which LED components need to turn on. So for example, if I put the number 1 in, 0, 0, 0, 1, actually let me clear this guy out. So now 0, 0, 0, 1, easy 0, 0, 0, 1, 1 comes on. So that means I want the components B and C to come on. So I have an AND gate that when I have not the 3rd bit, not the 2nd bit, not the 1st bit, and then the 0th bit, I need to turn on B and C. And if I wanted to turn on, say, 6, I would do 0, 0, I would do 0, 1, 1, 0, and I would get a 6. So, in other words, I have not the 3rd bit, the 3rd bit, not the 3rd bit, the 2nd bit, the 1st bit, and not the 0th bit. So 0, 1, 1, 0. And when all those conditions are met, I need to turn on the C, D, E, F, G, and A light. So I turn on A, C, D, E, F, G, etc. When F is on, that would be 1, 1, 1, 1. So when all these bits are set, I need to turn on the components that turn on F, which is A, E, F, and G. So basically, all these segments are all connected to this bus here. The decoder just outputs the correct value. I had to use diodes to prevent any kind of feedback going to the other components that shouldn't turn on. But yeah, and so by doing this logic, I can input any value I want. So 1100 is C, 1101 is D, 1110 is E, 1111 is F, and I can put them in either number I want. So this gives my computer the ability to output whatever it needs, up to 8 bits right now, and as you can see, my computer's 4 bits. 8 bits is a little bit limiting, but that LED is actually... There we go. That guy was turned off. So, for a 4-bit computer, 8 bits is pretty much all I need, but I think I'm going to go ahead and bump it up to 16 bits just so maybe I can start adding some error messages. Looks like I got a loose wire here, actually. As you can see, this guy likes to stay off. But anyway, there we go. So I gotta fix that little wire. But we have the number 98, which is 1001, 1000. If I put in F, that's 1111, 1111. I could do, C, F, which is 1100, 1111. So whatever I put in, I can just put in 1, 3. and again, there we go, 0001, 001113. So that's where we're at with this. Hopefully that was somewhat interesting. I will do hopefully more videos on this soon and explain the other parts of the computer, kind of how I built these at the transistor level if people are interested, and then hopefully kind of show off more capabilities that I have that I haven't shown off in other videos yet. So that's hopefully to come soon. Thanks.